let's do some more exercises. I think that will help. All right. So before doing that, I think it will be good to, well, take a look at some simulations, I guess. And it would be nice for those of you that still uh, maybe still confused a little bit about how things goes in terms of electric field, electric force, the electric field strength, and all this stuff. So you can actually go back to this category of electricity in the simulations website that we just looked at earlier. And there is another one that actually looks pretty good. Is this one here, which is the charges and fields. Okay, so you go back to the same category about electricity and magnets and circuits, and then take a look at the charges and the fields. So this one is also a good visualization. That's, I think that's better than just what we can just draw on screen. And this will give you an overview of what we have been doing in the first half of the lecture. Okay, so what you can do over here is, this is just like a blank space, and then you can just drag a positive charge here. All right, so you can see now the arrow representing the direction. Okay, and they use the intensity to represent the strength of the electric field. So as you can see, when you go further away from the charge, then the brightness of the arrow is getting dimmer and dimmer, right? It's getting smaller and smaller. So it's that representing the weaker field. Okay, so that's why when you are closer to the field, then the strength of the electric field is going to be quite big. Okay, looks good. Okay, so what you have over here is, I can put a sensor over here. That's nice. So this one will tells you the direction of the electric field. So if you sort of play around with this simulation, you can pretty much get a sense of what you're gonna get at each individual point. So for example, when I go further away, you can see that the electric field vector, the red arrow, is getting smaller and smaller, that representing the weaker field. When I drag this yellow dot closer, you can see now it's getting larger and larger. So that's a stronger field. Okay, and actually I can just go around. Oops, sorry. What did I do? It is my palm. Sorry, one more time. Ooh. Oh, it just hit the back. Okay, sorry. Okay, try again. So when I press the sensor there, you can see now that no matter where you are on this one, electric field from positive charge will point away from this. Okay, I can place many sensor there so you get a sense of what it is. Okay, point away from the positive charge that's generating it. And actually, you can now, if I place the second charge in here, then of course you're gonna get the net summation of the vectors of the electric fields generated from both positive and negative. So now things will go crazy. But okay, let me eliminate this one for now. Let's just look at just purely negative charge. So as you can see, now electric field will point towards it. I think I just have to eliminate some of this sensor. It's in the way a bit. Okay, here we go. All right, so as you can see, when you have a negative charge, electric field point towards it. So when they sort of move around the sensor, the closer you get, the larger the electric field that you're gonna get as well. But electric field always point towards, point towards the negative charge generating the field. Further away, the field is small. Closer, the electric field will be strong. But it's point towards it. Okay, looks good. All right, something like this. So I think it is a good simulation that you can play around, and actually there will be some other stuff that we can add on top, that we're gonna use this simulation one more time to explain what's going on next time. I think this is kind of nice. Okay, you can even put some sort of like the, oh, not the value, it's not the value, isn't it the value of the field? Okay, that's good. All right, so you can actually drag around, and then there is the value associated with it. But for us, because we don't know the distance, so the value might not really help much. All right, but this one will give you a sense of what is happening here. All right, and then when you combine this, you can go as crazy as you like. You can place a lot of charges on this one, and the vector that you get at the position of the sensor, that is the net vector summation of the electric field generated from those charges, okay, in the system. Okay, all right, so for those of you that's still confusing about the directions a bit and how the electric field is happening around a charge, maybe this simulation might help visualizing the field around it. Okay, all right, cool. All right, so this is going to be the main figure. Positive charge, field around it. Okay, very good. All right, so let's come back and let's do some more exercises. Okay, once again, I want to emphasize this. Force and field are related through just the charge. Place the charge in the field, you will experience the force. Just like you place a mass in the gravitational field, you experience the force. Okay, same thing, same concept. All right, so this one just give you an idea of how can you gonna get the force in the direction of the fields all the time. So this is a good example if you can generate the field, in this case pointing upward. Okay, so the field, electric field is pointing upward. And let's say that you shoot in an electron, the black dot here, perpendicular to the field. So it means initially this electron is running in the horizontal direction. So once you are in here, look at the black dot, the first one on the left. Once you're in here, this charge or this electron will experience the force right away because it's already entered the field. And because the field is pointing up, okay, let me write it here. The field is pointing up. It will experience the force equal to the charge times the field. However, because right now the charge is negatively charged, so the force will pointing down. You guys with me? That's cute. Okay, let me put like, because if it's an electron, so let me put it here. You guys with me? Okay, electric field pointing up. The charge is negative, so the force is opposite to the field. It's pointing down. So what it means is no matter where you are on here, you will experience this force at all time because the force is in the direction of the field. And you can see now this is trying to mimic or to copy the scenario when you throw a ball from the roof or whatever, from the bridge or whatever, and then the ball is just do the projectile motion down to the ground at the lower level and all this stuff. Yeah, sounds good. All right, so this one just representing that what is going on with the charged particle that try to move perpendicular to the electric field. It will be the same scenario when you throw a ball horizontally, cut through the gravitational field. You're going to get a projectile motion. Same thing. Okay, so just once again, just to confirm the similarity between electric fields and the gravitational fields and the behavior of the particle that moves around with it. Okay, but for the electric field, we are focusing on the charge. For the gravitational field, we focus on the mass. Okay, it's just different properties. Okay, all right, so it's sort of like come back in circle now. I introduced to you the electric field, but eventually I can go back and talk about Coulomb's law. This is a law that actually is a law that's saying what is going on between charges. All right, so this is a fundamental law that explains the force between two charges. So when you have two charges, Q1 and Q2, there is a force that acting between them. And I already mentioned that these are the action and reaction force according to Newton's third law. Okay, but now I can tell you right now that actually we can arrive to this Coulomb's law by, okay, here we go. I have Q1, I have Q2, Okay. Now I want to know what is the force acting on the Q2. What I'm doing is first I'm going to calculate the electric field at the position of Q2 first. Okay, here. Let me call this the E. Okay. So if you know that the distance from Q1 to point, let me call point P, here we go, is R. So the electric field at this point is going to be K Q1, the charge generating it, divided by R squared. You guys with me? Yeah? And because right now is a vector format, I have to say this is going to point in this direction as well. Point, let's say if it's positive, so it's point away from it. But then I want to get the force at point P that acting on the charge Q2, placing there. So I would say conclusion is the force on on the charge number 2 due to the charge number 1. Let me put like 2 1 subscript here just to say that's a force on 2 due to charge number 1. It's going to be simply you take the Q2, right, because you place the Q2 charge there, and then multiply by the electric field at point P, and that's it. You're done. And what you're going to get is going to be K Q1 Q2, see, Q2 just drop down here over R squared. And the direction is going to be in that direction. And as you can see, this formula you're seeing over here is the same thing as this one right here. So just want to confirm that the Coulomb's law, even though you can start from saying that this is the law that's saying what is going on between two charges. But what I'm trying to get to sort of like to present to you here is think of it as you have a starting point of one charge. Okay, this charge have the field around it, and then the second charge is in the field of the first charge, so it's experience the force of the charge times the field. So that's what my point is. Think of it this way. All right, but you can think in the opposite direction, of course, because the Q2 also having the charge of its own. So that's mean at the point Q, no, not use Q, sorry. At point O, there will be electric field at point O as well, due to the charge Q2. You guys with me, yeah? Okay. So the Q2 itself also generating the field at the position O. How much? Is going to be K Q2 over R squared. Okay, and it's in this direction right here. And if I place the Q1 at the point O, the force that I'm gonna get, force on charge number 1 due to the field from charge number 2, let me put the subscript 1 2 in here, is going to be charge number 1, because I place the charge Q1 at point O, times the field at point O. And that is going to be K Q1 Q2 over R squared in this direction. But you can notice that actually this is once again this dude right here. Okay, so what I'm saying here is this is the action and reaction force between two charges. And now you can think of it as charge number 1 generating the field at the position of charge number 2. So the charge number 2 can experience the electric force. And vice versa, the charge number 2 also generating the field at the position of charge number 1. So the charge number 1 will experience the force due to the field of the charge number 2. Done. They are interacting with each other through the field. Okay, through the field. All right, and then the K that we have been using all along, the constant that we say the Coulomb constant, it's this number right here, which is, well, we can use approximate number to be about 9 times 10 to the 9th. That's kind of like nice rounded number here. Okay, and actually this has a more fundamental properties associated with the K that we're going to discuss later on, maybe 2 weeks from now. So don't worry about this one for now, but don't worry if this k is going to be represented in another form, like 1 over pi, 4 pi, and then there is another constant. It's confusing, this one. All right, so you're starting with the k, which is constant already, but it turns out this constant can be written in terms of another constant. Wow, that's too many layers of confusions here. All right, but anyway, so don't be sort of don't panic just yet. It seems like there's so many stuff, but eventually 2 weeks from now you will see that, okay, this expression makes sense. I hope. Who knows? Okay. All right. Okay, so this is Coulomb's law, and I represent it to you through electric field multiplying by the charge. All right, but at the end, the shape or the form of this formula will look like this: K times the charge between the pairs interacting between each other divided by the separation between the charge square. Okay, sounds good. All right, anyway, that just wrapping up things, but eventually we're gonna have to come back and do more exercises. All right, so this slide is just exactly what I did here. Okay, which is maybe easier to just do that. Maybe there's one point that you might find it sort of like perplexing. Well, Ajahn, what is R hat? I think I'm not gonna speak about the R hat at this point. Okay, I want you guys to sort of familiar with the concept of the field and the force for now, and then we can throw in the R hat later, or maybe never. But for now, I think it's already good if you know how to determine the directions and magnitude of the field and the force. I think that's good. All right, don't worry about the vector notation at this point. Okay, all right, you guys try this. So we'll do a series of exercises one more time, and then we call it done for the day. I think it's heavy already, but I hope it's heavy at we attacking the same thing many times. So I hope the concept of this will stuck in your head. In the figure, 3 charged particles lie on an x-axis. Okay, particle 1 and 2 are fixed in place. Particle 3 is free to move, but the net electrostatic force on it due to the particle 1 and 2 happens to be 0 if the distance given, if the distance are the same, okay, L1, 2 and L sub 2, 3 equal, what is the ratio of the charge between Q1 and Q2? Okay, all right, so this is good. What do you think? 3 charged particles are on the x-axis. Okay, particle 1 and 2 are fixed. 3 actually is free to move, but then they move to the position that is already the same distance between L1, 2 and L2, 3. So, well, it's not free anymore. Just place it there. Confusing a bit. Okay, let's say it's free at first, and then they just place it there. Okay, they want to know if at that position it turns out there's no force. The net force on particle number 3 is 0. What is the ratio of the charge? First of all, that means the force on particle number 3 must be 0. Or the field on charge number 3 is 0. You guys with me? Doesn't matter you're going to get to the force or you want to get to the field. They must give you the same thing. So let's do that. So let's assume that the charge number 1 interacting with the charge number 3 and generate. Now, if I want to speak in terms of the field, let me call this field at the position 3 due to the charge number 1. Let me call E31. I don't know. We don't need to have a pair of numbers, but just to be clear, let's say this is the charge at the position number 3 due to the charge number 1. Let's use the double numbers, yeah, to represent the pair of stuff. Okay, so for this to be able to get down to 0, it means that the fields from the charge number 2 must be opposite in directions and equal in magnitude. So you are able to cancel these out. Okay, cool. So at least this gives you a hint that no matter what the charge of number one be, the charge at point number two should be opposite in sign. But we don't care because we only care about the magnitude. So what we want to do is we just want to compare the magnitude of the two. So the magnitude must be equal. Okay. All right, that's what we're trying to do here. Now let's start from the magnitude of the E32. What are you gonna get, guys? The electric field at point 3 due to charge number 2 is going to be K times Q number 2, the charge that's generating the field, divided by the separation or the distance from charge number 2 to point number 3. And that's L23. Let me name this L23 to be just A, so we don't have to write too many subscripts there. So it's going to be K Q2 over A squared. It's good. Very nice. And I'm going to equate this to the electric field at point number 3 due to the charge number 1. And because the charge number 1 is 2A away from point 3, so the field will be K, charge number 1 generating the field, divided by the distance squared. You guys with me? And that's it. This is good because we only compare the magnitude. K cancel. A actually cancel as well. So what you're getting over here is that's the final answer. Q1 and Q2 is just 4. And you're done. Which makes sense because we already learned about the magnitude and directions and all this stuff. That because the charge number 1 is further away from point number 3. So you have to compensate by having a larger charge, okay, to make the magnitude of the field equal to the field from the charge number 2, which is closer. Okay, now because we already learned about force, so I'm gonna redo these problems one more time by doing the force instead of the field. Okay, let's do it. So let's say, about Ajahn, I don't want to deal with the field. I want to deal with the force. Well, okay, that's fine. So let's look at the point number 3. Let's look at the pair of this one. First pair is 1 and 3. I can say there is a force acting on number 3 due to the charge number 1. Okay, okay. And what is the magnitude of this? It's going to be K Q3 Q1 over the separation square. You guys with me? Okay, this is the force acting on the charge number 3 due to the charge number 1. And according to the Coulomb's law, it's the K times both of the Q's divided by the separation square. I do the same thing between the charge number 3 and the charge number 2. So the F, the charge between the charge number 3 and charge number 2 is going to be K Q3 Q2 over separation square. And then I'm just going to equate these two. And as you can see, once I equate this, the Q3 will cancel. And then you eventually get back to this. Okay? All right, so that means you can do the field or you can do the force. They will give you the same results. It just depends on which angle of, you want to approach this problem. But eventually you get to the same conclusion anyway. Okay? All right, I hope I make my point saying that once you get the fields down, the force is straightforward. Okay, very good. Keep going. Try again. All right. Now you have 3 point charges that are arranged as shown in the figure below. Find the vector force on 5 nanometer nanocoulomb charge. Okay, this is good. They want to figure out the force on the 5 nanocoulomb, which is positioned at the origin. Very good. Now what I can do two ways now. Okay, but let's start from the new way a little bit because we were discussing about the force. So I'm going to show you how it's done if you want to go directly to the force right away. Okay, let's do this. First, we got force between charges. That means you always have to consider a pair of charges at a time. So let's start from 5 nanocoulomb and the negative 3. Let's start from this pair. Okay, because these two are opposite in charge. So they're going to exert an attractive force. Okay, attractive force. So 5, because now we're focusing on the 5 nanocoulomb. So 5 nanocoulomb is going to get dragged towards the negative 3. It's going to be the pull. Okay, attractive force. Okay, so let me name this force to be F number 1 right here. Okay, because we don't have numbers here. Okay, F number 1. Now turn our attention to another pair. So let's take a look at 5 nanocoulomb and the 6 nanocoulomb. But these two are now the same in charge. They're both positive. So they're going to repel each other. But because right now we are focusing on the 5 nanocoulomb charge, so the force due to this pair will be to the left. Let me call this F2. Okay, you guys with me? Okay, so let's do it one by one. F number 1, the magnitude of it coming from K. The product between the pair of the charges is going to be 5 nanocoulomb times 3 nanocoulomb. Once again, I don't have to bring the negative sign into the 3 nanocoulomb anymore because we have already determined the directions of the force. So all I need right now is just the magnitude divided by the separation between the two, which is 0.1 meter squared. That is the magnitude of the F1 force. Do the same thing with the F2. It's going to be the K times the pair of the charges, which is going to be 5 nanocoulomb and 6 nanocoulomb, divided by the separation square, which is 0.3 meters squared. All right, and that's it. That's it in the sense that you have to add these two together as the vector summation. So you need to use the Pythagorean theorem for that. There you go. That will be your sigma F right here. Okay, so that means the net force will be square roots of F1 square plus F2 square. Very nice. Okay, and that's it. The rest, just plug in the number. So many things. All right, but anyway, the point is, what you can start seeing right now is simply applying the Coulomb's law, and then you figure out the force vector, and then you just do the vector sum. In this case, that's why you have to get to the Pythagorean theorem to get to the final length of the sigma F. Okay, looks good. All right, very nice. All right, however, I can actually do through the electric fields if you want. Okay, so if you want to do the electric field, now you start seeing that, hey, Adan, we can calculate the electric fields at the origin first. With me? So that means what you're going to get is, instead of calculating the force, you calculate the electric field at at the origin first. So that means you could probably, instead of getting the F1, you're going to get the E1 instead. Okay, let me use the parenthesis. And instead of getting the force F2, you probably can just get the E due to the charge number 2 instead. And then once you calculate the net E, Then you do the net force through Q times net E. You will get the same answer. Okay? And this one you should, if you're confused, then you should try it. But if you sort of get what I'm trying to say, then okay, such just sort of okay, I take it. I take it that these two approaches pretty much the same. It's more like you want to jump right ahead into the force, or you just want to go like, okay, break into few first and then get to the force, but you're going to get to the destination no matter what. Okay, all right, I hope you see. But personally, I like the fields and then get to the force. I don't know why, but it seems like, well, I would say it's systematic in a way. It seems like it allow me to calculate the field first. So this means I don't have to worry, is there any charge at the point of interest? And then I imagine that I bring the charge toward the end of your of the calculation. But that's just personal preference. Okay, so that means try it if you want. Okay, calculate sigma E first. And then sigma F equal to 5 nanocoulomb sigma E, something like this. Okay, if you want to give it a shot, it would be great. It would be nice. Okay, try again. We have some more exercises. Here we go. All right, things getting more complicated, but it's still within the same sort of like concepts. In the figure, the particles have charges Q1 minus Q2 given to be 100 nanocoulomb. Q3 and Q4 is 200 nanocoulomb with the opposite sign. Okay. At a distance x given to be fixed at 5 centimeter, they want the x and y component of the net electrostatic force on particle number 3. Okay, so they're focusing on this. Here. What's going on with the charge number 3? That's what they want. Okay, so which one you want to go with? Let's go with my personal preference. So what I'm thinking of this one when I try to attack this problem, even though they're asking about the force on particle number 3, I am going to calculate the field at particle number 3 first. So that means in my imagination, that's how to do imagination. In my approach, I'm going to sort of like forget that there is any particle at point 3 at all. Just like forget about it for now. And just try to get to the electric field due to this charge number 1, number 2, and number 4. Okay? That generated at point number 3, at charge number 3 position. That's what I'm going to do. Okay, let's do this approach. So I'm going to get to the field first. Charge number 1 is positive. So the electric field at the origin is going to point away from it. Let me call this E sub 1. Here we go. Pointing down. Very good. Now the charge number 2 is negative according to this. Okay, so the electric field at the origin will point towards it. Okay, let me draw right there. Let me call this E sub 2. Very good. And charge number 4 is negative. So this one is negative. So electric field will point towards it. Let me call this E number 4. Okay, so what I'm going to do is I'm going to calculate the magnitude of each electric field and then sum them up in the vector format. Once I get that net electric field vector, all I need is just multiply by Q3 and I'm done. Okay, so first, magnitude of the E2 is, okay, you guys now should be, there is 1, 2, so let's start from number 1. So magnitude of electric field number 1 is what? K. Okay, Q1. Okay, I prefer to substitute numbers toward the end, just in case that there is some cancellations or, some factor that I can pull, divided by A squared. You guys with me? Okay. And this one, you can put a note that it's pointing down, even though we have the vector diagram on the left, but that's okay. That's good. E2 magnitude is going to be K. Q2, of course, divided by, of course, this is going to be root 2A because this is just a square. So the diagonal is going to be A root 2, root 2A. Okay, very good. So you have root 2A square. Very nice. And now electric field number 4 is going to be K Q4 over A squared. And that's horizontal. This one is 45 degrees, like that. All right, and now your thing is just do the breaking these vectors into components, like horizontal components and vertical components. It's gonna be tedious on this one, but as you can see, it's not too bad now in terms of execution because you already know everything. So what I can do is now breaking, it is only E2 that is not doing horizontal or vertical. So I'm gonna break this E2 into two components. There you go. Okay. So you're gonna have E2. You can do cosine 45, and then the horizontal one is gonna be E2 sine 45. It's 45 degrees, so sine and cosine are the same. Okay, so what I can draw the conclusion is going to be the net electric field along the x-axis first. Let's do horizontal. Is going to be the E2 sine 45. Yeah, that's the horizontal one from the E2 plus the E4. There you go. That's the net horizontal electric field. Do that with the vertical components. Net electric field in the vertical direction. You have E2 cosine 45 pointing up. But then the E1 is pointing down. So you do the subtraction of the E1. Looks good. Alrighty. So once you have this net electric field along the x-axis, net electric field along the y-axis, all you need to do is the net electric field vector is going to be Pythagorean theorem again. Okay. Okay, numbers is not going to be so nice here. All right, here we go. All right, and you just add them up using with the help of Pythagorean theorem. Yeah, you get the net electric field at position of the charge number 3. And then you can get to the final answer. What is going to be the net force? Actually, let me emphasize that this is, well, I don't know, you guys confused. Well, yeah, I hope this is good. Okay, let me write it like this. It's the same as net electric field vector magnitude. Okay, so every time you have a vector, you have an arrow on above the head of that letter, right? And then if you want just the magnitude, you just put the absolute sign in it, just want the magnitude. However, that is the same thing as you write it like this without any arrow on the top and the absolute sign. The meaning are the same thing. I know you noticed this. Okay. All right. So the force, net force, just the magnitude, is going to be, now you imagine that I'm gonna just place the Q3 back here, the red dot here. I'm just gonna bring it, boop, put it back there. That's my Q3. And then I'm just gonna multiply this with the sigma E that we just calculated right there. And that is the net force acting on the charge number 3 due to the other 3 charges. Okay. You guys kind of like quiet a bit, but I hope it works. Woo. All right. Yeah, content is pretty hard. Really, really, really hard. But I hope some of you that have done some physics like this from high school might find it okay. Right? It's just sort of like a review of some of the material that you have already done before. But for those of you that haven't seen this kind of thing at all, this is going to be quite a little bit of like need some time to get used to. Okay, so I think practice a lot will help. Okay, but I hope you see the two approaches that I'm trying to show you, but eventually it will get to the same final answer. Okay, but it's just your choice. Okay, any questions? Okay, if not, let's move on. Okay, now the next is going to be the last one. I don't know, this is a good place to try this or not. I just want to have to ask you guys, how do you feel right now? Is this already like too much? Or this is still like have some room to go a little bit further? I don't know. What do you think, guys? I just want to adjust the level of the material to be just about right. But what we have been doing today is just only force and field. That's it. All right, we haven't done much more than this. Pretty hard. Okay. So do you think you want it's confusing? Okay. All right. I got it. So I think you want me to stop here because the next one is calculus. If you guys still confusing about the concepts of the fields and the force, I think pushing you through this exercise will just throw in some stuff into the mix, and that will just going even further. But anyway, so what I'm gonna try to do is this. Okay, for those of you that sort still confusing about this, I think it's just listen to the approach that I'm going to do with this exercise. All right, but don't worry too much about the calculus because even though if this one is going to show up in the exam, it's gonna look something like this right away. And of course, I prepared a little bit of exercises, but we're not gonna try to push too hard today. So I think I am going to explain how to do this using calculus because that's the college physics. So I think it's kind of nice, and this is the place that you should see this. But for those of you that's still confusing, I think maybe you just have to listen to me like, you know, for once, and then we'll come back later and then try to study this again and again. Okay, so what I'm going to start up in this lecture is with the in reality you're probably not going to get this kind of system of charge distributed, you know, in space like, hey, 4 charges, 5 charges. Usually you will come in like, you know, a bunch of charges continuously distributed. Think of it that way. Right? Even though it's like tiny electrons, but once you bring in million, now you can think of it as like it's pretty smooth. You have like a super, like, you know, a bunch of charge lying around. So that's why we're going to look at what's happening when you have a chunk of charge. That's, you can think of it like it's a distribution that is continuous now. Okay, so what you want to do is you still want to stick with the concept of Coulomb's law, but you have to add on top with the calculus and to bring in some integral calculus and help you sum all those vectors for you. Okay, let's give it a shot here. All right, I don't want to speak about this formula right now. I think it's better to just look at an example. Here we go. Now, if I have an array of charged particle inside a rod, so this means this rod are filled with data. Any questions? Oh, okay. Okay, no questions. Yeah. Okay, all right. Okay, so if you have a rod that filled with bunch of charges, so this means these rods are charged rod. So it's a rod with a charged particle on it, and the charge are uniformly distributed across the rod. Okay, all right, very good. And let's say that you would like to calculate the electric field at point P, which is at the distance A away from the left ends of the rod. what will be the electric field there. That's it. Last example today. All right. Okay, let's go through this one. It's actually, once you've done it and you do it again next time, it's going to be quite easy, I think. But if you haven't seen this before, it's going to look difficult. Okay, here we go. So the way that it's supposed to be done is like this. When I say using calculus, is because this rod has a continuously distributed charge on it. So you have to determine what is happening at point P from a fraction of the charge. So you slice this into a tiny piece of charge first and hope that you're going to do it very, very small enough that everything approaching zero. So that means the amount of charge in here is going to be super small. That's very small. But it's not zero. It's close. Let's call the amount of charge in there to be some differential of the Q. Mini super small Q. Okay? So what happens when you have a mini charge of size dq and you are at the distance, here we go. I'm just going to mimic the whole thing here. There you go. See? So you can imagine that if you only consider what is going on between the dq and point P, you can calculate the electric field due to this dq to follow just the Coulomb's law, or just the equation to calculate the field that we saw before. Is going to be the K, the charge generating the field, divided by the separation square, or the distance square. And because right now the distance is already the distance that you can measure on the x-axis, I can say the distance is just x. And then you square that. Guys with me, yeah? Okay. And because this is the field that generated from a very, very small charge, I'm just going to call this, it's going to be very, very small field as well. So I'm going to say this is just a tiny differential of the electric field. Now, the calculus comes in. You're going to have to do this by slicing this into a tiny charge, dq, from the left end of the rod, and see what is the dE that generated by this slice. And then you start slicing next. And let's see what is the dE from this next slice. And then you keep slicing this, slicing this, slicing this, slicing this, slicing this, on and on, 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 on and on. And each tiny, tiny, tiny piece of the slice will generate a tiny, tiny value of the dE at point P. You guys with me? So what I need is, I want to sum them all. So I'm just going to do one first slice on the left. I pick up one dE. Do another slice. I pick up another dE. Another slice. I pick another dE. 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 And then eventually you're going to have to sum them all. Summation of something that is close to zero, that's the integration. So you have to do it from the left end to the right end of the rod to get to the net electric field at point P. And that's it. That's the setup of the whole thing that we're going to do. Okay, you guys with me so far? Okay, let me redo it one more time. So every time you see this, I'm just going to slice it into a tiny piece dq. And I'm going to say, okay, dE. Oh, let me do the blue. It's just k dq over x squared. I want everything from the left to the right. So I have to sum all this dq from the left end of the rod to the right end of the rod to get to the net electric field at point P. Okay? Now the last thing is, you cannot integrate this one just yet, because if I rearrange this equation a bit, k can be pulled out, of course, that's just a constant. But I have 1 over x squared to integrate. Everyone feel okay with 1 over x squared because it seems like you know how to do this. However, the integrating variable is not x, is q, which is not good. If you want to integrate any functions, it has to be the d of that variable. So what is dq อาจารย์บอก well, it's not the x, so you still cannot integrate this one just yet. So you have to somehow turn this into something of dx. Then you can start doing your integration under x variable. So here it goes. You said dq is just the amount of charge inside your slice. But actually, no matter how small you slice, it's gonna take up some space, some width. Your slice must have some width. So let's say the width of your slice is dx. Okay? So that means there must be the quantity that can relate the dq and the dx somehow. And that quantity is, we call it the lambda. But don't think too much about what John is another constant. No. Actually, if I'm asking you how much charge inside that width, you can tell me, Ajahn, this rod has charge per length to be a constant. And then let me name that constant to be lambda. You guys with me? You just say about Ajahn, the density of the charge on this rod is constant. So no matter what you slice it out, you're gonna get the same amount of charge if the length are the same. So let's define charge per unit length to be lambda. So there's no doubt why there is this word in the questions. The question already give you the amount of charge per unit length. So if you have the length of dx, how much charge should be in there? Lambda dx. You guys with me? Lambda is the charge per length. So it means if you have 1 meter, you're gonna get the lambda Coulomb. 2 meter, 2 lambda Coulomb. 3 meter, 3 lambda Coulomb. You just multiply the length with the lambda, you get amount of charge. So if you have the length of dx, you just multiply dx with the lambda, you get dq. That's it. Nice. So once you know the lambda, that lambda will help you convert the dq into lambda dx. You guys with me? Yeah. Okay, cool. All right, and now lambda for this problem is just another constant. So I can take the lambda outside the integral, and you only need to do the integration of 1 over x squared dx. Now everything is under x, your life is happy. You can set the upper and lower limits according to your problems. You can say that you want to integrate or you want to take the summation from the left end of the rod, which is when x equal to a. Perfect. Bing, 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 right here. And then you want to take your summation all the way to the right end of the rod, which is when x equal to a plus l. Bing, bing, bing. Very nice. And that's it. You can start doing your calculus that you have already learned. I don't know you learned from who. But it's 1 over x squared. It's easily done. The integral will be negative 1 over x. You guys still with me, yeah? Okay, the integral of x to the negative 2, you get negative 1 over x, or negative x to the negative 1. And you have the lower limit and upper limit there. And then you just do the upper limit and lower limit, but because I have the negative sign, so I'm going to get 1 over a minus 1 over a plus l. Done. That is the electric field at point P. ไหวไหมเนี่ย Woo. Alrighty. I hope it's alright. Alright, if not, you have to do it yourself for a few times until this thing sort of, it's all zero. Alright. Okay, so the approach is this. I'm gonna stop here. I think this is like, okay, at the peak of everything already. So I think the approach multiple times. So I think the approach is this. Try to do the exercises in this handout yourself first. Okay, it's sort of like, hey, start from zero, start from starting point, and then try to finish the whole thing. And then we have, as you can see, I think we have like 7, 8, 9 problems that we have done here. So I think just redo those yourself and see which point that you get stuck. Okay, and then let the calculus part to be, sort of like finale of the whole thing. Is this going to be in the final? If this is going to be in the final, I will let you know right away. Okay, sounds good. And the problem might just look like this. So don't worry if I'm gonna, add some, application of the calculus in the electric field calculation. Probably no. Okay, but if I just want to test your calculus approach to some of the problems, that problems will look like this. Okay, even though I have 2 more on the back, but don't worry about those just yet, because I don't want to bring you too far away from the concepts of the field and the force. Okay, I don't want to make calculus to be your burden that, done, because seems like it's purely mathematics, right? Because the concept already has been used on the first line right here. That's physics is already here. The rest, it's pretty much like calculus topping on it. So, well, I don't want to focus on calculus too much, but I think not showing you this, it seems to be not good. Because this might be the only place that you will have a chance to see this. So, all right. I'm not even finished Cal 1 yet. All right, so don't worry. If, okay, let me see. Let's say if this is going to be on the exam, it will look just like this with a very, very small alterations of the questions. Okay, so you can feel, okay, sort of like, okay, feel all right. Don't worry about it. Okay, I might even reuse this figure. Think of it that way. All right, so don't worry about calculus. Okay, and I'll discuss with Jantanet, and I'll try to stay away from it. Sounds reasonable? Okay, and if it's not gonna be away from it, I'm gonna tell you exactly what type of question is gonna show up, so you have time to prepare for those. Okay, but this is probably going to be the highest point of calculus based problem. We're not going to try to go anything further than this. Okay, but you need calculus because that will give you tools to calculate something for the next week as well. So that's why I cannot just, hey, forget about calculus, on and on. I think this is good. All right, we need some of this. Okay, just only enough. Whew. Okay, maybe I talk too much today. All right, but the material is getting complicated, understandable. So make sure that you try. I think that's the only thing that I can suggest. Okay, and then just come back to me if you have any questions. And I think this is a good point. So next week, I'm going to do the lecture live on campus. Sounds good? All right, so as promised, that we're gonna probably switch between online and on campus. And I think this is a good point to at least meet face to face in case that you have any questions. Okay, so next week will be on campus. However, you don't need to come to the class because once again we'll do the broadcasting just like last time. All right, should be good. Okay, sounds cool. All right, for those of you that want to meet face to face and then have some questions directly, then that will be welcome to stop by the campus. But for those of you that have to travel a couple hours to get to the campus, then you can still just do it at home. Okay, sounds good. Alrighty. Okay, if that's it, then I think I'm gonna stop here and then take care of yourself, and I'll see you guys next week. All right, and in the meantime, I will prepare the extra exercises just like before, so you have some more exercise to practice. Okay, all right guys, have a good week, and then I'll see you next week on campus.